going to hear about from Aaron Alexander, who is here today and is standing upright, which he had to do injury. So that's super awesome to see. Aaron is actually a PhD candidate here in the Department of Civil and Environmental Engineering, but he actually is also secretly a meteorologist. Not so secretly, but he has a bachelor's degree in atmospheric science and physics from the University of Nevada, Reno. And then after that, got a master's in civil and environmental engineering at UC Davis. But during his time at Davis, he worked on land-atmosphere interactions, particularly interactions between soil processes and boundary layer development, and has a few papers out on that topic. He's now joined the Steve Lohide lab here at UW-Madison, where he's been working on a really novel way to represent urban hydrology in atmospheric models. And so we'll hear more about that. Aaron is a very active graduate student. He's involved quite a bit with the American Meteorological Society. He was involved at the student conference recently and has been now co-chair of the recently formed Board on Student Affairs for AMS, helping lead more of those activities as we move forward and trying to better integrate students into our disciplinary society. So I'll leave it at that and turn it over to you. Better representation of urban vegetation alters surface water temperature cycle, titled with a conclusion in it. So
yes, it does have a conclusion. Thank you, and thank you everyone for coming to the first time I've worn pants in 8 weeks because I've been recovering from a knee surgery, for those of you who don't know. So thank you guys all for making it out here. So I wanted to start off broad, and for those of us here in Madison, we have an understanding of this, but we live in urban areas. About 50% of the U.S. population lives in urban areas, or 81% of the U.S. population lives in urban areas, with 50% of the worldwide population living in these regions. And urban locations are not static. By 2050, we are going to be seeing a larger expansion of these urban regions. And that means a lot of things, but for the perspective of meteorology and hydrology, this means that we're going to have more hazards that we need to be looking at. And urbanization exacerbates hazards that we would normally have in a vegetated location that we need to be caring about because they act a little differently. So one hazard that we need to look at is flooding. And we can look at how urbanization can increase flooding through the use of a simple water budget. Now, simple water budget means that we're going to have precipitation, and that's going to be balanced by the amount of runoff that occurs or the amount of water that isn't infiltrated into the soil. We have the amount of water that stays within the soil, or soil storage. We have the amount of water that is then going to percolate down and go to groundwater or deep drainage. And then we have the water that's going to be used from the soil storage and become evapotranspiration. There are other terms that are important here, and I'm going to be neglecting them for reasons that are going to become clear a little bit later. But in the simplified water budget scheme, if we look now at how an urban water budget occurs, we see that we've changed from a vegetated surface to an impervious surface. So something like concrete or asphalt. This means that runoff is going to increase drastically, and our deep drainage and evapotranspiration and soil storage are all going to decrease overall, but there can be patchworks of locations that are going to be much higher in urban areas. So this is something that can cause more flooding because enhancement of runoff is the main mechanism of how flooding occurs. And urban flooding is very much an issue. In Milwaukee, in a study done in 2014 or 2013 by Yang et al., there was a historical study that looked at 2 major watersheds within the Milwaukee area. One of them is the Menominee River watershed, and the other is the Cedar Creek River watershed. The Menominee River watershed is shown here on the top, and you can see that as the peak discharge we go through time, it starts to increase. And this is because this watershed itself has gone through a major urbanization process. More suburban areas, more buildings were added, more impervious surface. This increased the amount of discharge. Now, this isn't just a simple way of looking at this, because the actual flooding that occurs is very complex. So just because I've added pavement doesn't mean that that's going to be where the flood occurs. There's going to be infected water that moves through the impervious surface areas to create a heterogeneous patchwork of larger depths and smaller depths. This is a plot that I've taken from Ivanov et al. 2021 that was looking at flooding depths that occurred due to Hurricane Harvey. Now, Hurricane Harvey was a major precipitation event that you could treat as pretty homogeneous in terms of the amount of water that hit the ground, and we can see how crazy the actual patchwork of flood occurred within this watershed. Now, I'm going to shift gears a little bit, and we're going to talk about another urban hazard that you may or may not have heard about, and this is heat. And we can look at urban heat in the same way using a simplified energy budget. So we're going to look at the amount of energy that is coming into the system, or is going to be net radiation. And this is the amount of radiated energy that's coming from the sun and the overlying atmosphere that has been balanced out by what is being reflected back into the overlying atmosphere. This generally is going to be balanced by ground heat flux, which is a storage term, sensible heat flux, which is the amount of radiated energy that goes to change specifically air temperatures, and the latent heat flux, which is just another way of looking at evapotranspiration. Note that I also have other terms here because this is a very complicated area of research, and if you want to know more, please talk to Dr. Desai, who's in the room, because there's a lot that goes on there. Now, when we go to urbanized locations, we change again the surface from vegetated to be pavement. And this causes two big things. We're first changing the thermal parameters that are going to be at the surface. So this is going to be changing our heat capacities and our albedos and emissivities. That's going to allow us to capture more energy. And this is going to cause also a reduction in latent heat because we have less energy that can go to vegetation, and we also have less vegetation to evapotranspire. Now, this is something that many of you may have heard of because we've known about this since the 1890s. It's called the urban heat island effect. Changes in evapotranspiration or decreases in evapotranspiration and modulations in our thermal parameters cause an increase in air temperatures in urban regions compared to non-urban areas. And just like urban flooding, this is not a homogeneous process whatsoever. In a study that was just done in the Milwaukee area during the summer of 2022, there was sensors that were attached to cars that were drove around the Milwaukee Metropolitan Sewerage District's area of interest, which is shown here, and they were able to capture the diurnal changes of temperature throughout the city. And then using some statistical mapping, they were able to get this, which we can see is quite a complex patchwork of differing temperatures. This was the map that was done around midday, but there are 3 other maps that you can find within their report that is freely available for everyone to see. I would like to draw everyone's attention to the northern part of this map, where there are locations that have drastic temperature gradients between lower air temperatures and higher air temperatures. Near the shore, we have the location of really, really hot air temperatures, which is quite interesting because that's not something that you would think would be there. And then in the more urbanized area near downtown, we have this really hot air temperature location with little speckles of lower air temperatures. And we also know that urban heat islands have a clear diurnal cycle and seasonal cycle. In a study done by Schatz and Bouchard in 2014, which was done right here in Madison, Wisconsin, they were able to show very clearly that there is more urban heat island effects at the nighttime, and that it is most predominant during the summertime. So this makes sense from the simplified energy budget approach that we were looking at, because more net radiation means more energy to be captured, which means more temperatures can be changed. So we know that there are hazards in urban environments. The question that we now have to ask is, how can we adapt to these urban environments? And how can we adapt to these hazards in urban environments? Well, one way we can adapt to these is through the use of green infrastructure. Now, I'm going to be using the term green infrastructure throughout this talk. There are other ways of talking about these. It could be low impact developments, it can be nature-based solutions. You'll find literally a paper that was published in 2014 that has about 1,000 citations about different ways to say green infrastructure in the literature. So, I'm going to say green infrastructure. The goal of green infrastructure from a hydrologic perspective is to take a city and try to return it back to what it used to be. So we want to try and have this be hydrologically very similar to the surrounding watershed that a city is nestled in. So for our purposes, when we're looking at this means that we're going to be increasing tree canopy, we're going to be using downspout disconnection, we're going to be adding in green roofs, and we're going to be adding in permeable pavements. If we look at each of these implementations by themselves, we can have an understanding of how these are going to affect a microclimate around them. So, for instance, if I were to go and add 20 more trees in a city park, I would have an understanding that that's likely going to lower the air temperature in that surrounding area. Or, to shout out one of my co-authors, Carolyn Boder, if you were to do a full downspout disconnection at an urban parcel of a single unit home, you could see large changes in the urban water balance of that location. But we have questions now about what happens when we try to adapt widespread green infrastructure on the scale of a city. For instance, if we look at Milwaukee Metropolitan Sewerage District's green infrastructure targets, we can see that this is something that is not being captured within the literature. We're trying to make changes on the order of adding 50 square kilometers of tree canopy, adding 39 square kilometers of downspout disconnection, adding 6 square kilometers of green roofs, and adding 5 square kilometers of permeable pavements spread all across Milwaukee County. Also note that this is going to be paired with reducing the amount of paved area by about 40 square kilometers as well. This is a drastic change that we are going to be seeing in the Milwaukee area, and we don't really have an idea on how this is going to be changing not only the system-wide or the city-wide hydrology, but also the city-wide energy and potentially even the regional climate. And that's where my team that I'm working on and my PhD kind of steps in, where we're trying to understand how all of these interrelate with one another. So jumping into this talk, the objective of this talk and really my PhD research is trying to quantify the changes in urban water and energy balances at the surface that are going to be associated with green infrastructure. And we're going to evaluate how these changes then affect atmospheric responses. So this means that we need to have things that are going to be able to represent urban processes associated with green. I'm going to get into those more a little bit later, but we're really trying to explicitly represent the important surface hydrologic processes. And that is something that is very much lacking currently in regional climate simulations. We also want to have easy integration into regional climate models. I'm going to spend just a little bit of time on that point because I usually talk to a lot of surface hydrologists and they're like, why do we need to use a regional climate model? Well, a lot of times we think of the atmosphere influencing the land. So rain falls, flood happens. But there's an equally important link that occurs where you can make small changes to the temperature of the surface and that feeds back into the atmosphere and can make precipitation more probable. This is what we're looking at and trying to understand with this research. So we need to have both the atmosphere influencing the land and the land influencing the atmosphere. So we're also going to need to have an understanding of how do regional climate models currently deal with urban environments. And there are a lot of different ways, there are a lot of different climate models, and we're going to be broadly putting them into 3 basic ways of dealing with an urban region. The first is a SLAP model. This means that they're going to be looking at trying to get the 0th order issues of urbanization. This means we're going to have decreased permeability, we're going to have decreased albedo, there might be some changes in the aerodynamic roughness, nothing really crazy. Then there's a widely used model called the single layer urban canopy model or the single layer urban canyon model. Same acronym, just slightly different wording. This is trying to get the mean changes in both radiative processes and fluxes, as well as changes in winds. So you're going to have a representation within the actual model itself of an urban canyon where we have roots, buildings, and ground, and that's going to cause changes to the radiative fluxes. And then we have this is a relatively new addition into the sphere, but a multi-layer urban canyon, where instead of just having a single layer, we have multiple layers where we can have turbulence closure and try to get secondary circulations within this simulation. This is a very computationally expensive model itself, but there's emerging group of papers that are using this to try to understand more localized effects in urban areas. Now, one thing I have not mentioned whatsoever in this talk so far, or at least on this slide, is urban vegetation. Urban vegetation in regional climate models is often an afterthought. It's not usually integrated. It might be in as a single green roof parameterization. There's no representation that I know of urban trees within any regional climate model, which is pretty big oversight because it's pretty ubiquitous in lots of urban areas. So we need to have something that can adapt and have urban vegetation. We also, if you recall, have to care about urban heterogeneity. So when I think about urban heterogeneity, we need to be able to represent all the little small facets that are occurring on a climate scale. So in typical urban models, we take a complex urban environment, we simplify that down to a single land type, and then we try to solve that on in a land surface model on long time scales and on larger spatial scales. This is really easy to solve and makes it great to work in climate models. Problem is this is really simple for the kind of effects that I've outlined and things that we are kind of going to look at. So there's another way that we can take this, where we can start looking at something called a mosaic scheme. A mosaic scheme takes now this complex urban environment and breaks it down into multiple land types. So instead of just having one, we can have four, we can have six, we can have eight. We solve all of these through our land surface model, and then we take an average of the outputs to then feed into our grid that then feeds into the atmospheric circulations and the atmospheric applications. This gives us a better representation of urban heterogeneity, but it does not have something that is really important, which is urban eco-hydrologic interactions. That's just a fancy word for saying sometimes we have land types that overlap one another, especially in urban environments, that we need to care about. For instance, let's think about this means that we have no viral water transfers. So this can be shown here, at least in this complex urban environment diagram. Let's say that we have water that is being intercepted by a tree, and underneath it is actually a pavement. How do we represent that? Or say we're trying to be a good Samaritan and we want water to move from our house and move onto our turfgrass. There's no way to represent that currently in land surface models. This is something that if we're wanting to capture the spirit and important hydrologic processes of green infrastructure, we need to be able to integrate. So that's where I've come in and I've done a lot of work on this. And we have a new land surface model that is based off of NOAA-NP, and we're calling it NOAA-NP for heterogeneous urban environments, or HUE, because everything needs to happen. This is going to be taken and takes in representations of eco-hydrologic interactions for specific land types that we built. This is an urban tree, a tree that overhangs the pavement, urban turfgrass to turfgrass, or urban permeable pavement to a permeable pavement. And we flux water from one side to the other, and we'll do this in a mosaic scheme. So this means that we now have the ability to start transferring water, which is the point of green infrastructure. Transfer water from someplace that we wanted, or we don't want it to someplace that we wanted. And we can then start to solve the climatic style problems that we're interested in. The big pro of this is that it includes viral water transfers. Just to make sure that we're all on the same page about viral water transfers, because they are a very big, important part of the story that I'm about to go into, want to make sure that we have an understanding. So, urban tree. This urban tree is going to be vegetated. And let's say that we have some pavement that doesn't have any tree that overhangs it. If that is going to have all the water or rainfall become runoff. If I were to then have a little bit of this tree overhang the pavement, in normal land surface models, I wouldn't be able to calculate any evapotranspiration flux because there's no tree base here. What this model does is it takes water from the soil here based on a area scaling and fluxes it into the atmosphere for us. This is a very similar process that occurs when we have urban turfgrass. Any water that falls onto this pavement, it takes a fraction of it that we can set for full disconnection or half disconnection and puts it onto the turfgrass. Effectively, what this looks like in model world or on this grid is that we have some land types that are able to communicate with one another. So 1 to 2 can communicate, but we wouldn't be communicating 2 to 5. This allows us to start to get at this green infrastructure problem and still works within the land surface model sort of space. Now, let's jump into some results and see what impacts this can have just on a single grid square. I'm going to be showing simulations that were taken over 3 years that are occurred from 2018 to 2020. As you know, I probably have been heading it a little too hard, but I've been focusing on Milwaukee, Wisconsin, because they have a very aggressive green infrastructure plan. And we're going to be looking at results from urban tree-to-tree overhang and downspout disconnection, so urban pavement to turfgrass. We do have results for urban permeable pavements, but I want to get to looking at some climate model simulations a little bit later, so this is what we're going to have. I'm going to be pulling out specific simulations that are going to be representative of a typical land surface model, which is how that very funny picture of a tree that's been cut in half and has no tree overhanging. That's how a typical land surface model would deal with this aspect of if I had a flux volume of 50% tree, 50% pavement. Then we have an extreme case that we're looking at. Say if we were looking at a single neighborhood parcel where we had a lot of tree that was overhanging pavement. This is always going to be shown with this icon. And then we have something that's in the middle. So say we're at the city scale, and we can say on average we have up to 10% that of tree overhanging pavement. This is always going to be shown with this icon. We traditionally think about green infrastructure through the lens of event-based runoff. So that's the first thing that we're going to look at. Here in blue is the amount of runoff for every single storm that happened during the growing season for my simulations. So over 3 years of simulations during the summertime, every storm that happened. Blue is showing how much runoff occurs. Gray is showing how much runoff extra occurs. You'll notice that every time that we have a storm, we have more runoff occurring without that additional tree overhanging pavement. And we can look at that even a little bit more, where we look at a percent difference between the depth that had fallen and how much it was reduced by. And you'll notice that there is a tailing off that occurs. This tailing off is directly proportional to the amount of extra tree canopy that we have. So if I were to add, instead of 35% extra tree canopy, 50% extra tree canopy, we would see that this line would level off at around 50%. So this inherently makes sense and is a good gut check for us. We don't want to be wildly changing the amount of runoff that's occurring for this specific land type. Now, I also promised that we're going to look at downspout disconnection. So again, we have a system that has no disconnection, which would be a very naughty person in terms of the urban hydrology. You should let your water go onto your turfgrass, especially if you live in Madison. It's very important. This is going to be letting your water that falls onto your roof just go directly into the pavement. So this is no disconnection. Then we have full disconnection, or letting all of the water go onto our turfgrass. And then we have a 50-50, where sometimes it goes, or sometimes some of the water, about half the water goes onto the turfgrass and half of it doesn't. So we can look at this again. These are the same exact storms, but we're now looking at the amount of runoff that occurs from a full disconnection and no disconnection. The same story is there. We always have less runoff occurring from our treated pavement or our treated flux volume compared to our non-treated flux volume. This is how green infrastructure works. This is a good gut check. And importantly, you can notice that we are tending towards complete reduction for this case. This means that at storms that are on average less than 5 millimeters, which are trace amounts, but still a little bit of rainfalls, will have no water enter into the stormwater system first. And that is on the order of what we would expect for this underlying climate. So if we do a cross comparison of the event scale of hydrology for this, we can see that we do okay with the extra tree canopy simulations. Downspout disconnection is sometimes best. But we don't only get to look at green infrastructure in terms of event scale hydrology, we also need to look at it in terms of seasonal scale hydrology. So we're now going to shift gears a little bit. I don't know if it's become clear or not, but I am a big fan of very complex figures, so we now have a walkthrough on how to read the next figures. There are bar plots, and you would think bar plots are going to be easy to understand. They're really not that easy to understand, so I'm sorry, thank you for attending. So runoff is always going to be shown in blue on the next figure, and the darker the blue, the more likely it's related to a pavement. So darkest blue, water's coming off of the pavement. Lightest blue is going to be coming from vegetation, and in between blue is going to be, there's going to be tree that's overhanging the pavement. That's the portion of the flux volume cares for. Evapotranspiration is going to be shown in green, where we have tree over the yard and tree over pavement following a similar color pattern. We have deep drainage, which is going to be going the amount of water that goes to percolation or to groundwater recharge shown brown, and soil moisture storage, which in this case is always negative, and is going to be shown in green. So we can compare and contrast our three tree canopy simulations. And first we can look at the amount of runoff that occurs. If we take runoff based over an average growing season, we see that we've reduced runoff. That makes sense, especially since we just looked at the event scale. And we are reducing by around 80 millimeters, and most of that reduction is coming from the actual paved surface. Notice that for our surface runoff that comes from the yard, that's relatively stable. We also know that there is an increase in evapotranspiration, where we can see that there's an increase in evapotranspiration. And this is coming because we're actually adding in extra tree canopy. While not shown here, we've done another test where we keep the amount of tree canopy the exact same, and we just move it over to overhang our pavement. And these results are relatively stable in that case. So it's not just that we're adding more canopy to flux water, we're also increasing the thermal loading on this part of the tree canopy that has pavement underneath it, so it needs to evapotranspire a little bit more. Finally, rounding off the rest of our fluxes, we have a slight decrease in deep drainage, just meaning that we're using more water, and a sharp increase in soil moisture deficit. So that means that we are using more water, so a lot more water is being partitioned into evapotranspiration. We can also look at the same for the downspout disconnection. This story is much the same in terms of runoff. We have drastic changes in the amount of runoff that's occurring. And though the individual portion of the surface runoff that is from the vegetated portion increases, it is still not enough to overwhelm or overcome when we don't have any downspout disconnection whatsoever. We have a marginal increase in the amount of evapotranspiration. Note that this is going to be something that's going to be very climate dependent. In Milwaukee, we are not in Milwaukee, during the seasons that we looked at, we were not stressed in terms of soil moisture. So if we were to take the same simulation setup and go run it in Oklahoma City, Oklahoma, or Phoenix, Arizona, this would be a very different picture in terms of evapotranspiration. Most of our water is going to be partitioned into deep drainage in this case. And then we are going to see a response in a reduction of our soil moisture deficit. This means that we're going to be returning to where we started from in terms of our soil moisture time series. So looking at the growing season water balance effects, runoff and evapotranspiration have similar signs, different magnitudes, but the actual story behind deep drainage and soil moisture storage are different. And that's important because different impacts of green infrastructure or different green infrastructure can be used for different purposes throughout the city. Now, I've also promised a little bit about energy cycles. So we're going to now look a little bit more at energy cycles. This is a very heady diagram, so we're going to walk through this very carefully. I have sensible and latent heat fluxes that I plotted on a diurnal pattern. I've taken every single day that occurred during the simulation for the summertime during 2018, 2019, and 2020, and collapsed them and averaged them by the time of day. So when you look at this, you're seeing the median shown in a dark line, and then the interquartile range of the sensible and latent heat fluxes and where they peak throughout the day. This is the profile that we get if we look at our typical setup. This is the profile if we look at our expanded setup. Note that sensible heat flux peaks have gone down, latent heat flux peaks have gone up, and they become more variable. If we now just look at those peaks and look at every simulation that we did, we've done over 71 simulations in this case, we can see that we have a marginal marching decrease in the sensible heat fluxes, while peak latent heat fluxes continue to increase, but they also become more variable. This is pointing to the fact that we have the more covered of pavement is going to be helping us reduce sensible heat fluxes, while evapotranspiration is going to be more dependent upon soil moisture storage. Now, we can also look at the same sort of idea for downspout disconnection. Downspout disconnection, this is our typical, this is our fully disconnected. You might be like, wow, are you showing the same photo? No, I'm not. They are slightly different, but very slightly. This is where that question of the underlying climate comes back into play. Again, if we were going to be making changes, say in Phoenix, Arizona, this would look very different, but because we are in a location where we're preferentially going to deep drainage, the energy fluxes are not going to be changing that much. So, this is the growing season energy balance effects. We have large effects that occur for a tree canopy. We have smaller effects that occur for downspout disconnection. So far, we're about 30 minutes in. Everyone should be going wild and crazy. We have seen urban processes associated with greening and how they change with urban water. This has been basically looking at the leg of this process so far, the atmosphere influencing the land. We haven't had any variability going the other way yet. And we see that we can generally reduce runoff. With tree cover, this causes changes in enhances evapotranspiration and reduces sensible heat fluxes. For downspout disconnection, this enhances deep drainage and causes very small changes to energy. But again, different climate, we would have different response. So now, finally, the whole enchilada that I've been kind of trying to get to at this entire time, what happens if we let the atmosphere start changing as well as these? Well, we did some simulations using WRF. WRF is a regional climate model. It stands for the Weather Research and Forecasting Model. We've done a 2-domain simulation where we have domain 1 at 9 kilometers, domain 2 at 3 kilometers, and we're using year 8 hourly boundary conditions at domains. This, I'm going to be showing kind of a typical 10-day period that occurred during the longer simulation that I'm still piecing together what exactly is going on, but the story is still there that we can start to see some of these changes. We are, of course, going to be centering in on Milwaukee, Wisconsin, and if you would like to know more about the specific physics parameterizations that I'm using, please talk to me afterwards. I have a very scary table that we can all look at, but I didn't think anyone else wanted to look at that during this talk. I'm going to be showing off 3 WRF simulations. The first WRF simulation is going to be termed typical, and this is going to be using what we would normally do if we were doing a regional climate simulation. So this means that we're going to be using the urban companion model that I described earlier in this talk. This is always going to be shown using a black or dark gray line and be known as typical from now on. I'm going to be also using a mosaicing scheme approach. No lateral water transfers are being added, just a simple mosaic scheme, and we're going to be using GIS to process land types in the land. Everywhere else in our domain, we're using the same data set from the National Land Cover data set from 2016, and this is going to be known as mosaic. We're going to get a little bit more into this in a second. And then we're going to have simulation 3, which is the whole enchilada. We're using lateral water transfers, we have new land types, everything is happening. And this is going to be known as Q. I mentioned that there are changes in land use. years. So if you were able to see the poster that was there while I was recovering from surgery at the Bryson Scholarship poster session, or if you saw me at AGAMS, I was talking very, very loudly about this. But what we've done in changes or in simulations 2 and 3 is gone through the GIS data sets that are available in Milwaukee County, and we've been able to get the extra land types that we need to run NoMP here. This means that we have estimates of how many buildings and roads don't have any canopy that are overlapping, or how much in terms of area buildings and pavement are covered by canopy, how much turf grass there is, how much urban tree there is, how much water there is, just in normal times. Note here that we're using turf grass as a residual, so there are some locations where turf grass is probably not going to be the most realistic. But we can still pull out trends from this. If we look in downtown Milwaukee, we have heavily urbanized areas. In the northernmost part of Milwaukee County, where we saw this intense urban heat island effect way back in the beginning, where you're probably being like, that was still the same talk? Yes, we're still here. We saw a lot of tree canopy, and then we have a lot of turf grass, it seems like, in this lower part of Milwaukee County. This is actually not true. This is actually a mosaicing of some city and a lot of agriculture. So in this location, I've assimilated in NLCD data to have a representation of the agriculture that's there, and most of this turf grass is now actually canopy, or is now actually part of that. So that is kind of the story that we can tell from a single data. Finally, let's look at some air temperature. Yay, woo, time series. So we are now looking at WRF simulations that have taken the entire county and I've collapsed them down into a single time series. We have our 3 simulations, and the dark line again is showing the median, and the shaded is showing the interquartile range at every time step. What can we tell from this? Well, there's not that many differences so far, but warmer daytime temperatures happen to be typical at the peaks. If you look on the 11th of August, you can see that it's warmer. This also occurs in the 10th of August, as well as on the 16th, 17th, and 18th. We can also see that there are sometimes warmer nighttime temperatures within the hue and the mosaic schemes. So this is most easily seen on the night of the 15th, right when we get to the minimum of air temperature. We see that the mosaic and the hue simulations are generating warmer air temperatures. Perplexing, but there is a reason behind this. If we look at the central heat fluxes for this over the same time series and use this using the similar averaging approach, we can see that in times that we have a higher mean central heat flux, we have a higher mean air temperature, a typical value, and at nighttime when we have slight deviations in the central heat fluxes going slightly lower in the typical simulation, we have lower air temperatures. So everything kind of still makes sense in our gut check, so to speak. But looking at a time series doesn't give us anything in terms of the spatial pattern. So I also wanted to look at spatial patterns. We're going to only be looking now at spatial patterns that happen during the daytime, because nighttime from this is a little bit of a funky story that I'm still trying to piece together. I'm going to be showing daytime temperature changes, so anytime that there is sunshine that's occurring or our solar radiation is above 10 watts per meter squared, we're going to be looking at spatial patterns. And red always means that the other simulation is going to be warmer, and blue means hue is warmer. If we look at typical minus hue, so the typical simulation minus our hue simulation, we can see that there is patches of where we've changed our land use to be patches of where we've changed our land use and added in these lateral wire transfers are warmer in our typical simulations. The representation of lateral wire transfers is actually changing the air temperature in these locations. So that means it's going to be relatively cooler in those areas. But probably to most scientists in the room, they're asking why, for the ever loving hell, is this blue, right? Well, we can look at mosaic minus hue, we see that it is still slightly blue, but there's not that much blue. It's actually much clearer on not this projector, but on the computer screen. But the temperature difference in locations that are outside of Milwaukee are pretty much negligible. And this is because when we add in a mosaicing scheme, we're not just getting dominant land types, we're getting extra land types that are underneath, and more likely we're hitting urban locations. And those small changes in urbanization are going to cause drastic changes in air temperatures within regional climate models. So, even though this is blue, meaning that we have a warmer model overall, it does make sense when we start to compare and contrast our mosaic scheme. I also wanted to look at humidity, and my favorite way to look at humidity is dew point temperature because it's very similar to temperature. Higher dew point means that there's more water, lower dew point means there's less water. If we look at this time series, again, this is the average amount or the median time series taken over the space and our interquartile range, we can see that hue is not often more moist than our typical simulation. I went through and actually calculated this, and the percentage of time that hue is moister or more moist, or the time that typical and mosaic are moister than hue, there's a lot of moisture going on, I apologize, is over 50%. Strange, but we'll get there. If we look at the latent heat fluxes, which kind of was our gut check for latent heat flux, or it was our gut check for air temperature, we have a much higher latent heat flux. We only have times that are around 16%, 13% of the times are there higher latent heat fluxes. And this is going to be on the marginals or around the actual edges of the distribution in our canopy, which I'm showing here. If we look again at the dew point differences, we see that there's more moisture in our hue simulations where we made most of our changes, and it is moister than the typical within the actual simulation or the actual outer area. And this is very similar in terms of our changes that we saw in air temperature. I'm just flashing typical minus hue again up here for reference. But there are subtle changes. If we look, there's this location that is, for some reason, even though we made changes, it's cooler in our air temperature, but it's also less moist. That's weird. We also have water that seems to be convecting down. And anyone who has had the pleasure of living next to a water body knows that the next thing we're going to be talking about is the sea breeze effects, because that's likely being modulated from this. So for those of us who don't know what the sea breeze is, that means that over a water body, we're going to have, during the daytime, a relative high pressure system. And over in Milwaukee, because of the temperature differences, we're going to have a relative low pressure system. That means we're going to want wind to move from high to low. Always really easy with physics, try to go from highs to lows. So if we examine now what the shoreline averages are for windrows, we see that we have not only less strong winds coming in our heat simulations, so that temperature gradient has been reduced, so there's going to be less, or it's going to be less force behind our winds. We also have some slight changes in directionality. This is further supported if we look at inland Milwaukee. We have less strong still coming in, and we're also less likely to return for our heat simulations. We don't have that return effect that's occurring. So we have likely less mixing and a very complex system where still, again, trying to parse through this. So we can look at the effects of coupled surface meteorology with, we have nearshore cooler temperatures. Nearshore, there are some moisture conditions that's very complex, and we have a less intense sea breeze. All of these are coming from small changes that we've made in the hydrology. And I think that's pretty cool. So, we're almost to the end. I'm going to give you guys a teaser of what's next. So, the next steps in my work are going to be trying to not only understand the surface hydrology and the surface meteorology, but also some boundary layer meteorology. This is the planetary boundary layer average potential temperatures over Milwaukee County. You'll see that there are two that are very similar to one another, our typical and our mosaic, and then we see that there is a outlier that is going quite crazy. That's you, trying to understand what's going to be going on there. This does not just mean, or does not, these effects aren't only occurring on typical days. If we look directly after this time series, this is a rainstorm that happens on the 20th, and you guys are looking at the same sampling rate, same time step throughout all of these. You'll notice that hue, mosaic, and typical all create very different representations of rainfall. So, what does this mean for us in terms of green infrastructure? Are we actually going to be making it more wet in Milwaukee by adding in more green infrastructure? That seems counterintuitive. We have a lot to dig into, and it's very exciting. But we're not only going to be looking at this in model world, we're also going to be doing comparisons with measurements because we can base this in reality. So there is temperature gauges, or there are weather stations throughout Milwaukee that we can use, a very dense MMSD rain gauge network that is taken at very high frequency to allow us to do analysis on rainfall spatial patterns. And we are living in the modern era, so why not use some remote sensing data? We also, at the last part of my research, and the final part of what my dissertation is going to bring, is we partnered with the Milwaukee Metropolitan Sewerage District, and we're going to be taking their green infrastructure plan and use this new tool that we developed and create scenarios for them to try to disentangle all of the changes that you can make, not only in hydrology, but in energy. And with that, I thank everyone for attending this. I know that that was a wild ride. We went through a lot. I'm going to drink some water, and I would like to take some time to thank the Hydroclimate Extremes Research Group and the Hydroecology Research Group, both groups that house me in the Water Resources Engineering department. It's wild to have an atmospheric scientist on your team, but I appreciate you. Thank you.
Time for questions. Start with students.
So, very interesting talk. I have one quick question about the mosaic transformations. You
Sure.
showed earlier that you classify one big thing into 8 sub-classification. When you actually deploy your model, how do you come up with the distribution of the classification? How do you know that how much 1 to 8 proportion you want to keep? Do you use satellite imagery for that, or it's random?
So right now what we're using is Milwaukee is really awesome, and they have LiDAR data that some poor intern back in 2020 took that LiDAR data and made shape files for me. And I have shape files that I'm able to do really simple differences. So eventually what we want to get to is being able to use satellite remote sensing data or something that's more broadly applicable to get at those extra land cover types. But right now, we take a couple shape files, we do some differencing on our actual grid that we're going to be projecting in WRF space, and we get the fractional amount of this much is a building, this much is a road, this much has a canopy over this road, to be able to then feed into that.
Okay. Thank you.
You're welcome.
Good questions.
Yeah, really good talk. So I had a question on, so you have this subgrid surface hydrology, right?
Yes.
And that would be coupled to, I'm assuming, grid-to-grid water movement also?
So that's great. That would be the next step after this research. In land surface modeling world, because, and in regional climate modeling world, because we have to solve on multiple processors, it's easiest right now for us to have land types that are within the single grid square communicating with one another. So if you remember back, I can flip to this. The land types that are in this square are going to communicate with one another, but there's no communication that's going to be happening at the surface between these two grid squares. So land types that are co-located with one another, they can talk, but the coupling that's occurring broadly is coming from atmospheric coupling, land atmosphere coupling for functions. Does that help?
Yeah, so I was wondering how would like flow of water through the city be represented? Like how does that work out within this framework?
Fabulous question. So that would require us to use something like SWIM or Hydro, where we would have information about channels. that then would have an overlay routing scheme. That is, again, the next step potentially that is not being represented here. We're doing this in a very typical land surface modeling approach where if runoff occurs in that grid, we take account of it, we're like, great, there were 2 millimeters, and then it's whisked away to numerical no man's land and waves over.
That brings up an interesting thought for you, which is that suggests your model could have a scale dependency on it, right? So the grid size you select, right, which influences what can communicate, there's a trade-off between fine scale representation and variability versus being able to account for that water transport. Have you thought of, you show 3 kilometers in this, and there are probably a number of reasons for that, but was there some thought process behind choosing 3? Because obviously if you got down to say, tens of meters, then this thing kind of doesn't quite work that way.
Totally. This wouldn't work the same way if we were up 10 meters. The original proposal was to do 1 kilometer grid spacing, and that just turned out to be so computationally expensive for us on what we were trying to do. But there is, you are correct, going to be some sort of grid scale dependency at some point. This is not going to be a useful scheme. But when we're doing global climate models and regional things at this order, this is a useful approximation. Other questions? I know that was a lot.
Steve?
So something I've always wondered about the question of urban heat islands is, as you showed, if you add more tree cover, for example, you get more evapotranspiration, the humidity goes up, the temperature tends to go down. But what's the trade-off in terms of heat stress? Because if you add more humidity, if you lower the temperature, it's not clear that that's actually helping with the human comfort level.
That's true. So it also, that is very dependent upon the climate that we're doing. So it's not very viable, but again, if we increase the amount of tree canopy in Phoenix, Arizona, we would have to use so much water, but that would be great because everything would be air conditioning. I'm originally from that part of the US, so we actually use swamp coolers instead of air conditioners, which just evaporates water into the air, which is awesome. So fuel efficient. But here, that's going to be a question that I'm actually pretty interested in looking at. There has been some work that's done in Chicago where they do not see they see major changes in the air temperature, but the actual thermal comfort is going to be very dependent upon the synoptic meteorology. So day to day, you might not see that big of a difference, but if we have a giant heat wave that comes through, you're going to be seeing a difference in human comfort. It's going to keep things much cooler. So you might, it's a very nuanced question that you ask that I can't really give a big answer to, but yeah.
Anything else? Alright, well, you know where to find Aaron.
Yeah.
Has apparently more slides that go deep into the
We can go if you want.
but
Probably not
let's
today.
give